the very first talk is on astronomical data approximation based on neural network models. It is by Samorodova Ekaterina, currently a master's student in cosmic research in Lomonosov Moscow State University. So now I request the speaker to share her screen.
Hello everyone. My name is Ekaterina Samorodova, and I'm a master's student of Lomonosov Moscow State University, specializing in space research. And I'm happy to have an opportunity to present to you the research on the topic of the astronomical data approximation based on neural network models. In my speech, I would like to touch upon the following points. First, topicality of the research. Second, the tasks set and solved. Third, comparison of the results. And after that, I will make the conclusions. So I'd like to begin by the motivation to study light curves of astronomical objects. It is a well-known fact that modern astrophysical catalogs contain billions of records, including light curves, radiation flux observations, which can be useful for solving different astrophysical problems, such as astronomical objects classification or peak intensity prediction. Classification tasks can be accurately solved with spectroscopy methods, but this analysis requires resources and time. And that is why machine learning models trained on light curves can be applied. In this respect, it is important to develop light curves research methods. One of the main problems is the presence of gaps and uncertainties in observations, which makes it difficult to use machine learning to study light curves. And this problem can be solved with data approximation. As it has already been mentioned, there are many problems that would benefit from using machine learning methods. For example, peak prediction is highly important for studying the physical nature of processes inside the stars. Currently, various methods of data analysis for solving classification problems are used, frequently trained on the simulated datasets. This work discusses the usage of various neural network models for approximation of light curves from plastic dataset compared to the existing approach based on Gaussian processes. In this case, the approximation curves are used for supernova 1A type identification and radiation peak time estimation for measuring the quality of the considered methods. The dataset used in this work is PLAsTiCC, containing synthetic simulations of future legacy survey of space and time for transient astronomical objects. For this work, a minor part of the simulations is taken for a faster assessment of models' quality. And now let's look at the tasks set. At this stage of work, it is necessary to determine the problem to be solved and the methods of solutions assessment. At this point, each light curve is considered as a function of two parameters, the time of observation and the passband value, one of the 6 possible photometric LSST passbands. Therefore, the task is to train an approximation model to predict flux values and estimate the uncertainty of the approximation at each point. This can be achieved while minimizing mean square error. After fitting the approximation model, a uniform grid of 500 timestamps values is fixed for each filter. Thus, a two-dimensional array of values is constructed for further usage in classification and peak prediction problems. An example of procedure outcome for a light curve fitted with a Gaussian process regression is shown on this slide. Gaussian processes mentioned on previous slide are most often used to solve the regression problem on astronomical data. The main idea of this approach is to expand the original light curve by adding new observations from a regression model. In order to test possible improvements, several models have been selected in this work for comparison with the Gaussian processes-based solution. The first model proposed in this study is the Multilayer Perceptron model from the scikit-learn library, which contains 2 hidden linear fully connected layers and uses the LBFGS optimizer, which converges faster than others while fitting to the small input dataset. In this task, the training subset contains about 100 records, and this is the reason why this option seems to be an optimal one. The second model studied in this work is the Bayesian neural network, which can be viewed as a generative model for available functions. Optimal architecture of this model consists of two linear layers with the normal prior distribution for neural weights. One of the main features of the Bayesian neural network is its ability to predict both target value and its expected uncertainty. Finally, normalizing flow is explored. It is a generative model following the distribution of a light curve while training. The main feature of this model is that it aims to reconstruct full probability density distribution. The flows are aimed at producing invertible reconstruction. And now we are moving to the model's testing stage. The next step is to define the quality checking conditions. For this aim, each light curve is divided into train and test sections. After that, each model is trained to predict radiation flux values. Then, models predict values on a regular timestamps grid with 500 values for each passband, as is shown on the slide. Two graphs show approximated values compared to the training values in the left and to the test values in the right. Now let's pass on to the comparison of the results. As has already been mentioned, some models are able to predict both approximated values and their uncertainty. Therefore, the next step is to compare prediction uncertainties for different models: Gaussian processes, upper right corner, Bayesian network, lower left corner, and normalizing flow, lower right corner. As could be seen, the Bayesian model predicts the lowest uncertainty values, while Gaussian processes estimation is too wide for large gaps. Normalizing flow seems to predict uncertainty stripes of optimal width. On the next stage, the approximated values are directly compared to the observed ones using a list of metrics. The obtained metrics are shown on the slide. The average time required to obtain a complete set of approximated curves is also reported here. Thus, neural networks provide results similar in quality to Gaussian processes, while approximating a set of curves with the NLP model requires thrice less time. It is obvious that one of the main aims of this research is to make the problem of astronomical objects classification easier to solve. First of all, light curves are expanded with the use of approximation models. Secondly, gained predictions are represented as a two-dimensional array of numbers. These gained arrays will be collected and used further on as an input data for the convolutional classification model. In this slide, you can see a typical transformation for the light curves. A clear structure of all the 6 passbands can be seen in the bottom slides. The classification model is trained on 60% of the approximated light curves and tested after that on the last 30%. The main aim of the classifier, whose architecture is shown on this slide, is to detect supernova 1A type using approximated light curves. The classification quality is also measured with a number of metrics. The next step is comparing classification quality metrics for the input data obtained with different approximation models. As could be seen from the table, light curves expanded with neural networks are divided into two classes with a similar level of quality as was obtained by Gaussian processes. While normalizing flows produced superior quality using regression metrics, the classification mutilates this leadership. In addition, to test the approximation quality, the volumetric peak prediction problem with two solutions is used. The first approach is summarizing all 6 approximated lines and defining the time which corresponds to the maximum of flux sum as peak time. This method can be used for datasets without any known true peak times, which is a common case for real observations. Otherwise, a regression model can be trained to solve this problem efficiently. We trained the convolutional model for peak prediction based on the approximated light curves. The architecture of this model is presented on this slide. All expanded light curves are divided into train and test subsets, and after that, both methods are trained on the first part, and their quality is measured on the second part. After that, quality metrics are computed. The resulting quality metrics of peak prediction methods for all approximation models are shown on this slide. Quite expectantly, the CNN-based model is superior in quality compared to the direct method. Besides, the Normalizing Flow model shows the best quality for direct methods and is similar with Gaussian Processes regression quality in the case of using the CNN-based model. In conclusion, I would like to say that in this work, various neural network models for light curve approximation have been studied and compared using different metrics and their uncertainty values. Neural network models have shown comparable approximation quality to the basic Gaussian processes solution. The scikit-learn model with NBFGS optimizer demonstrates the best approximation quality and speed. The source code, the testing results, and the usage examples of approximation models can be found in the full repository following the link on the slide. So, Ed, that brings me to the end of my presentation. Thank you for your attention. If you have any questions, I would be pleased to answer them.
A lot of thanks to Ekaterina to present this very beautiful work of her. So now questions, please. As far I cannot see any question on the Discord channel, so we can have questions from the room here unless we get some questions. Okay, so I can't see any from the room as well. So there is one question from my side. Maybe it's very vague. But how well is your technique suited for the data which is having very a huge data ununiformity in the data gaps? How well it can take care of?
Sorry, are you asking about fitting models on data with large gaps?
Yes, exactly. Thank you.
Okay, I want to show again one picture. So in the upper right corner, we can see that Gaussian process regression shows two wide stripe for the blue passband in the end. While other models like Bayesian neural network and normalizing flow models show rather not so wide stripes, and so these models are more suitable in this case for data with large gaps, I think.
Okay, thank you. Now we have two questions on our Discord channel. So very first is like, why do the RMSE looks so big? I mean, above 1.
Sorry, I have many tables and I can't understand whether this question is about this table or other metrics table, but I can say that that we use not RMSE as a key metric, but MAPE metric as it shows more understandable value that can be easily so I think that we will answer this question on the Discord chat more precisely.
Yeah, that would be great. So another question I want to take, like, did you compare against the 2D or 1D Gaussian process, a GP on the each band individual or fit all together?
So the comparison of different modifications of Gaussian processes regression lies outside this research, but as far as I remember, this comparison would be somehow presented in the future publication.
Okay, perfect. I mean, we can have further discussions on the dedicated Discord channel for this particular talk. Thanks a lot.